All right. Good morning, everyone. So it's my great pleasure to welcome Dr. Lulu to our machine learning seminar today. Dr. Lulu is an assistant professor in the Department of Statistics and Data Science at Yale University. He received his PhD in applied mathematics from Brown University, where he also obtained the master's degree in engineering, mathematics, and computational science. And after his undergraduate study at Tsinghua University. So Dr. Lu is a leading researcher in scientific machine learning, known for advancing both in the theory and numerical method to bridge the scientific machine learning and the physical science. He has acquired a few pioneer contributions in this field, including the deep operator neural network. So his achievement has been recognized with the DOE Early Career and MIT Technology Review Innovator under 35. So with that, we are honored to have him here to present the latest research. Please join me to welcome Dr. Wu.
Thank you, Chief, for that introduction, and thank you all for coming. So my research focused on a central challenge in computational science, simulating the complex dynamics of physical systems. So here I show you a few examples I have done in the past years of simulating the systems of different scales. From small scale simulation of rock gel, Gibson-Weld, RFDs, to large scale simulation of materials, airplane, or even large scales of carbon storage, climate, or even formation of a star. To simulate all these complex dynamics, so we can apply traditional physics-driven scientific computing methods, such as finite elements, molecular dynamics. However, as we know, these simulations are usually really expensive, especially for large-scale systems. Moreover, in order to perform this simulation, we have to have a complete understanding of the underlying physics. For example, we have to write down all the equations in order to perform simulation. And meanwhile, nowadays, people do data-driven machine learning. We can do machine learning for learning dynamics. For example, by neural networks. But purely data-driven machine learning could be expensive for data set, and we have collected a large data set for training. Also, in general, it lacks interpretability and generalizability. However, in many science and engineering applications, both the physics and also data may be imperfect. We may have some data and some physics. That's why we developed a new machine learning paradigm called physics-informed machine learning by blending data and physics. But in physics-informed machine learning, the data could be dinky, dirty, dynamic, or deceptive, which is non-perfect. The physics we consider can be any scientific domain knowledge, physical principles, constraints, symmetries, equations, or simulations. So we aim to develop scientific machine learning or physics-informed machine learning to be accurate, also to be efficient, scalable, and especially recently I focus a lot on robustness, generalizability, and reliability. So in this talk, instead of learning a specific function, which is mapping from RD1 to RD2, we will go beyond function learning to operator learning. So as we know, standard function learning for the theory is guaranteed by the universal approximation theory back to 30 years ago, almost 35 years ago. For example, a well-known method for the physics-informed networks, where we apply a machine learning neural network to learn the solution of the PDE, which is learning a single function. But in operator learning, specifically, we consider a mapping from one function to another function. And the functions are in the infinite dimensional space. So this is the fundamental difference between function learning and operator learning. Here I just show you a few very simple examples, but we can consider the derivative mapping from xt to the derivative function x prime t, or simple integral. But in general, I work a lot on PDEs. Then the mapping from different boundary condition, initial condition, force interns, coefficients of the PDE to the solution of the PDE which is operator. Or we can also consider the inverse operator from the PDE solution, the measurements, to infer the missing coefficients, missing terms in the PDE. More broadly, this concept can be applied to diverse applications in different areas beyond physics. Could be even biology, social science, and so on. So now let's look at how can we do operator learning. So this is a very basic framework. Let me introduce a few notations. Let's consider the operator I try to learn is denoted by the G. Bu is the input function of the G, and the GU is output function. So as GU is a function instead of a vector, so Y is a point in the domain of GU. Then GUY would be the function value GU, so the function GU evaluated at this location Y, which could be a point value or could be a vector. So given these notations, let's say if we try to learn a network, and this is a network, mapping from this function U to this output of GU. So how can we do that? Let's go step by step. So first, as U is a function, or we cannot put a continuous function, infinite dimensional space function, into my laptop. In computers, everything is discrete. So in the first step, we have to have a finite dimension approximation or representation of this input function U. There are many ways to do it. So here, just a simple way I show here. For example, we can consider we have a set of points x1, x2, until xm in the domain of U. Then the ux1, ux2, and the uxm, these are function values of U at these locations. But it could be meshed points or could be unstructured points. So this is a finite dimension representation of this input function U. But if m is large, the difference between the two is small. So this is the input function. Then similarly, for this output function, we can also predict this output function GU at finite locations. But here, we try to avoid this discretization. So we try to predict the GU at any location of Y. So the way we do this is by adding another input to this network called Y. But Y is location. We add a query location also as network input. Then the network prediction will be this function value at location Y. Now, after training, we can predict the GU at any location. Will be indeed a function. Also, the advantage of doing this is that it's pretty flexible, right? It's mesh-free or discretization-free. It can be handled, can be applied to handle diverse data sets, structured mesh, unstructured mesh. Also, for this kind of framework, where if you have some background on physics informed networks, or in general, when you try to apply this network for learning a PDE. So we can embed the PDE into the loss function of my training. Basically, PDE residual will be a part of the training. Then in order to evaluate the PDE loss function, we have to compute the gradients. But in PDEs, we always have gradients. So by adding Y as another input, then this gradient can be computed by automatic differentiation or backpropagation in deep learning. There's no error for computing derivatives. This will be another convenient. So, but this is just a general framework. Now let's look at what can we design, how can we design this network architecture? So this is one of our earlier work for deeper net. So in deeper net, the idea is pretty simple. Because we have two inputs, then we have two subnetworks. The branch net takes the U as input and outputs one embedding. And the core net takes Y as input and outputs another embedding. But then we merge these two embeddings to compute the output. And in deeper net, the way we merge the two embeddings is through a very simple dot product. So which means the output GUY is equal to summation of BK TK. So BK is the embedding of branch, TK is the output of the trunk network. So this is pretty simple. But this has lots of connections with the traditional scientific computing methods. For example, so TKY, as you can see, is only a function of Y, which can be viewed as a set of basis function in this output space. But here, instead of manually construct a basis function, we apply network to learn automatically what's the optimal basis function. Then the BK would predict the coefficients in front of the basis function. So this is our network architecture. Although you can see this is pretty simple, but actually we can show this is also a universal approximator for learning nonlinear operators. But I didn't have the theory details here. This is not the focus of today's talk. Let's go to one applications. So this is one application in geoscience called carbon sequestration. So here we have different wells, and we inject CO2 into this subsurface to store the CO2 for a long time. This process can be simulated by the PDE. Wait, somehow this is a delay. By the PDE showing in this slide here. So it's multi-phase flow in porous medium, but the subsurface can be modeled as a porous medium. And we have multi-phase flow, we have gas, we have water. So here, this is the key equation. Actually, this is a large set of equations. In order to simulate this, we can apply traditional methods by difference, by element, but they are quite expensive. First, because it's multi-physics and multi-scale problem. Also, we try to simulate these dynamics in a really large scale. For spatial scale, you can see it's 160 kilometer by 160 kilometer by 100 meter. Large 3D space. Also, the prediction time will be 30 years, a long time prediction of dynamics. So it's quite expensive. So that's why we try to train a machine learning to predict this. In the training, we have both data and physics, because the purely physics training will be quite challenging. So we also generate data set. So here I just show you one example in the data set. So the data is 3D, but here I just show you the 2D cross sections for easy virtualization. So on the left, these are all the conditions, the inputs to the network. So we have different field conditions. For example, the permeability field, porosity. Also, we have the scalar inputs, the speed of the injection of the CO2, the pressure, temperature, and so on. Then on the right, this is the prediction at different time. This is the gas saturation, this is the pressure. So basically, we try to train a network with this input on the left and with outputs on the right. We can apply one network for training, but you can see this will be quite expensive. We have 3D in space, 1D in time, in total 4D dimension. So one way we try to reduce the cost is using this idea of mesh refinement in traditional scientific computing methods. But here, basically, roughly speaking, we have a few levels of network. So we have a level 1 network, sorry, level 0. So level 0 predicts the global solution in the entire domain by in a coarse mesh, low resolution. Then if we zoom in to the location near this injection rate, while we have the fast dynamics and complex solution, we apply a second network to refine the resolution, refine the solution. Then we go to a few more steps. So by doing this, we can still maintain a good accuracy, but with much lower cost. And specifically, for each level, we have a single network. And this network is similar to what I discussed earlier, the depot net. But here, instead of doing the dot product merge operator of the two branch nets and a branch and two nets embeddings, we apply a few more layers of neural network. Specifically, here the network layer we applied is called Fourier layer in the Fourier neural operator paper. So basically, we apply this, roughly speaking, this can be viewed as a decoder. And this branch and neural networks is most like encoder. So by using nonlinear decoding, then we can predict more complex dynamics. You can see because the linear way of dot product is how to have complex dynamic prediction. So this is one modification to the architecture of the network. This one. Oh. Okay, thank you. I think okay, that's okay. Okay, now let's look at the prediction. One example. This is just a single example of the training of the prediction of new conditions. So here we have two wells. Then we can zoom in to this injection location in the well. This is a reference solution. This is a prediction. It's pretty accurate. But this is not surprising. As we know, if we have a sufficient large data set for training and with lots of cost, we can have a good prediction. So this is the one testing case which is interesting of extrapolation. So in the training of the injection rate, injection speed, it's small from 0 to 1.6. Then after training, we try to predict what if the injection rate is larger from 1.6 to 2. So here this is a result. You can see for small injection rate, we can have a good prediction for sure. But even for the larger injection rate, the red box is this extrapolation setting. The blue box is we also train the network using the larger injection rate. So the error definitely is larger, but still we can maintain a good accuracy. These results it's pretty surprising because by default, our network is not able to extrapolate, especially from low speed to high speed. But here somehow we can have good prediction. In our paper, we have more testing extrapolation results like this, but just show you one example here. So that's one application. But in many cases, after you train this network, you try to apply the train network for some other downstream task. For example, optimization. But this is another application of topology optimization of the channel. So this is a 2D channel. And in this 2D channel, we have two inlet velocities from left and from bottom. So we have two flow. The two flow have different concentrations. Now you can see if nothing inside, then this is the concentration. This is the pressure of the flow. But now we try to design this topology or geometry of this flow structure, of the domain structure. For example, we had some area block here, or we have 3 blocks here. Then these different geometries would lead to different solutions, different concentration field, different pressure field. Okay, so what we try to do is design the topology to achieve some specific objective. For example, we try to make sure in downstream task, the concentration field is well mixtured as much as uniform. So this is one objective. Also, we try to have another objective is energy consumption. So we try to maintain a small pressure drop from the input to the output, so we have minimal energy. The final objective is weighting summation of these two, weighting by omega here. And so we try to optimize this topology. The topology is either 0 or 1. 0 is solid, 1 is fluid. So it's a binary function. Okay, so this is a pretty standard topology optimization setting. Now let's see how can we do this by using deep learning. So first step, we generate some data set, do some random generation of topology, then we run this RANS simulation, generate a solution of the concentration and the pressure. But then we can train a network. Again, in this case, we also apply the free deep net. So the input will be topology, also the inlet velocity. But we try to make sure my network works for different initial boundary condition of the velocity. Then this is output of the concentration and the pressure. Now this is the first step of the training because it is pre-training. Then after training, this network is fixed. Then we go to the second stage. We try to search for this optimal topology to minimize this objective function. So the way we do this, we represent this topology also by a network. So instead of a 0, 1 and the matrix, it's also a network. So the input is coordinates and also different velocity, but because for different velocity, we have different optimal topology. So my network predicts a continuous field. Then we do a sigmoid to convert the continuous function to binary function of 0 and 1, fluids and solids. Then we put this topology gamma into my pre-trained network.
then my network would predict concentration and pressure, then we compute the objective. Then this one is fixed, but then we do backpropagation to minimize or to train my network of topology. So this is the second stage of training. But one challenge here is the runs simulation is expensive. The data generation is expensive. So initially, we only generate a pretty small data set, a few hundred. Then by using a small data set, for example, if you consider the velocity 0.1 and the weighting coefficient 0.1 and 1, these are optimal topology we found. You can see this definitely not the correct solution. For example, for omega equals 0.1, this is a really small, solid area in this domain, which it does not seem reasonable. So we know this is not correct. The reason is our network for training, our network data set, or the data set for network training is small. My network is not perfect. That's why it has this error in my final solution. So what we do is we can do active learning. But based on this solution, we have an idea. We know my optimal solution should be something like this. Then we can do random permutation or add some oscillation into this, my current optimal, to generate a small data set to refine the network training. Then we can have a second result. Then we can do another round. So by adding a small new data set, we can refine the network and also refine the final prediction. So you can see through 3 rounds, now the solution is almost converged. And this is my final solution in round 3. And here I show the initial training data set for these 2 objective pressure drop and concentration uniform metric. If they are here, but my final prediction for different omega is here. So you can see we indeed can achieve better objective compared to my random geometry. Okay, so this is
quick question about your step 1.
Sure.
Back to your method part. So can I think that as step 1? I think it's the previous slide probably.
Yeah, here.
Step 1, yes. So is this part like we try to build a surrogate model for solving the
yes, the surrogate model, yes.
And it's a nonlinear equation here, right?
It's nonlinear. It's turbulent. It's turbulent simulation. Yeah, yes. It's runs.
Okay. All right. Thank you.
So actually, dynamics. Although here you can see I plot a smooth curve. Actually, simulation is turbulent. It's pretty common dynamics. This is the time average. So it's average over time. That's why it's smooth. Okay, the next step is, okay, we have this optimal solution for my machine learning. What is correct in reality? So we do this 3D printing. We print this material, this topology. Then we do the experiments. We use a camera to measure the flow. And this is the real data from the experiments. Again, this is time average data. Then from this data, we can compute the objective, for example, the variance of the pressure. And this is the default smooth channel, but there's nothing inside. And the blue line is the machine learning prediction. The orange line is the experiment. They are pretty close. It's not perfect because there's always a gap between simulation and real experiment. And this one is my optimal topology. You can see we have a significant improvement on the variance of the concentration, and also the prediction is pretty good. So this is verified by experiments. Okay, so these 2 examples, they are complex, but still they are in the simple geometry. I mean, the total domain is just square. Now let's try to go beyond a square domain to be more complex than geometries and manifolds. For example, we can consider a PDE, which is the PDE defined in a triangle with a notch. So this is a complex geometry, but the dipole net I mentioned in the very beginning can be applied to this setting directly. Because, as I mentioned, but in dipole net, we have arbitrary correct location, so they can handle non-square geometry by default without any modification. So this is one testing example. We predict the solution from different boundary conditions. So the testing boundary condition, this is the prediction error. Okay, this is accurate, but let's go even further. Instead of a PDE defined in a complex 2D or 3D geometry, let's consider another type of PDE defined in a manifold. So this is a type of PDE. It's not defined, for example, this is a rabbit. It's not defined inside this all the domain of the rabbit, but it's only the surface, which means when you compute derivative, it's a derivative in the tangent direction of the surface. So this is called a PDE defined in a manifold. So similarly, we can also apply this framework to this type of PDE, but there's some modification required. For example, when you try to compute the PDE loss for training, we cannot use standard automatic differentiation. We have to develop a specific derivative computation graph for computation of derivatives in this case. But it's doable. We can also achieve good accuracy, but this is purely data-driven training. Purely physics-driven training. So no data at all, only training from this PDE physics. And here's another example, also complex geometry, which is hard. This is real geometry. So this is the left ventricle of a patient. So my collaborators have a data set of more than 1,000 patients. So each patient has different geometries of the left ventricle, and we try to solve a PDE on the surface of this left ventricle. This is the key equation, which is have a diffusion and some reaction, some forcing here. But actually, this is coupled with a larger scale OD system because it's a current in this PDE. And in order to simulate this current, it has more than 100 ODs. So essentially, it's a larger scale system. For example, to solve one case, it requires 3 hours in 48 CPUs for solving. So again, here we try to train a network, a machine learning, as a surrogate model, but to predict the solution of the PDE on the surface, but for different geometries for different patients. Okay. Yes, the idea here. So this is data-driven learning. So when we try to have a data set and apply data set for training, because my network cannot take different geometries directly as input. We have to have a way to encode the geometry into some space, then to do prediction. So this is a simple example to show how can we handle different geometries. So for example, in 2D, we have different geometry in 2D. Then let's assume we have a canonical geometry, let's say circle. Then we design a mapping phi theta and phi theta inverse, so map between my circle and this complex geometry. And for this mapping, there are different ways to do it. For example, we can apply a method called LDDMM. So this method can establish a transformation from one geometry to another geometry. Then this transformation is represented by this latent vector called theta. But then this would be one network input. Then everything else is the same. Then after training, but this is a testing case, we apply to a new patient. Okay, there are 3 testing cases. For different patients or different location, we apply the source term, roughly speaking. And this is a PDE solution. Then you can see this is network prediction, this is 0.1 error. It is pretty accurate. So this is a real example of complex geometry. Now let's go slightly to a different topic. So here I have shown you a few applications, actually 3 different applications to address different challenges by developing this operator learning framework. But what we have done, especially in the data-driven case, but if we try to have a data set for training, we are always on the left domain. We have many pairs of the data set, of the data points, then we do training. But now let's consider one extreme case. We only have one single data point, one single PDE solution. Now we try to train a network from this single PDE solution, then do the prediction for new conditions. So I call this as one-shot learning, one-shot operator learning, because we have one training point. So first thing I will try to convince you, this is in general mission impossible. This cannot be done. The reason is, in my setting, although I assume this is a PDE, but let's say I have no idea what's the formula of PDE. So PDE formula is unknown. So we cannot do physics informed training. We cannot apply any solver. Also, let's consider in this case specifically, so for example, we try to predict from this forcing term of the PDF to the solution of the PDE called U. With only one single data point, with there's no actual information. You cannot do transfer learning. You cannot do meta learning. This is the only information we have, nothing else. Foundation model, impossible. But we assume in this case, we do not have it. Okay. Oh, especially if you consider this is only data we have. Then with this data, if you try to do a linear regression, even for linear regression, you need 2 data points. With 1 data point, you cannot even do linear regression. Now let's see how can I solve this impossible task by using one knowledge we have in physics or in PDEs. It's a locality. Let's say we have a PDE defined in this square domain. Then if I do a random cut of a local small domain, then I know, okay, my PDE is still valid in this subdomain. Not the boundary condition, but I mean the PDE formula itself. But if it's a vector in the entire domain, it's still the vector PDE inside any domain, subdomain. So this is because in the PDEs, all the derivatives is only computed locally. So this is the only information or knowledge I try to leverage to develop the methods. So how can we apply this knowledge? So we try to go to the local domain instead of the global domain. So let's say we have a local domain. This local domain can in different shape, rectangle, triangle, or some complex polygon. They're always doable. But for the demonstration, let's assume it's a rectangle. Okay, we have a local rectangle. And then we draw a mesh. We call this a local mesh. We draw a local mesh in this local domain. Then all the points in this local domain include 2 parts. One is the point on the boundary. Another point is the point, let's say, inside the domain. Let's assume we know the PDE boundary condition on this boundary. Well, let's assume we know that. We know everything on the boundary. So the PDE solution UX on the boundary. For the boundary points, I call this as auxiliary points. Then also we assume we know the F. Actually, we do know it. The reason is in the setting. Okay, we try to predict a solution of PDE for any F. So F is always given. F is my input. So given the F and also given the boundary information, let's assume my PDE is well defined in some sense. Then I can predict the solution inside this local domain to determine the solution. This mapping exists and unique. But let's assume that my PDE has these properties. Okay, so let's denote this mapping as a G tilde. I call this as local solution operator. Well, it's a solution operator in the local domain. Now I try to learn this G tilde by using a network. So I have a network. So my network input has 2 parts: the boundary information, also the F of the entire subdomain. Then output is the solution inside the domain. Okay, this is my network. But how can we have a network, a data set for training? What we do is as follows. We have this solution of the global domain. Then we can look at any random locations as a sub-local domain. For example, I can put local domain on the left, the top corner. Then from this left top corner, we can extract the information on the boundary here, the forcing here, and the solution here, which becomes one pair of data set for G tilde. But this can be a uniform mesh, or it could be just do it randomly. Then we can have another location, a second data point, another location, another data point. Then essentially, from one global domain, we can generate a lot of data points for the local domain. Then we can train this G tilde. Okay, that's the first stage. So G tilde is well trained. Now let's see, once we have this pre-trained G tilde, my G tilde is pre-trained. Now, but for a new F, how can I get the global solution of this new F? we cannot do this to one end-to-end prediction. So we need something else. We have different approaches in the paper, but let's say a specific method that we call as lion. Let's say for new F, my PDE solution is U. Again, I use a network to represent the solution of the PDE. So I have network input different coordinates, some random location of coordinates, output is a solution of PDE U. Okay, then basically we plug in this PDE solution into my pre-trained G delta to compute loss function. So this is a loss function at any local domain. So I can input the boundary information from, for example, for this subdomain, we have the boundary information from G delta, we have the F, which is given, so my G delta would predict what the solution inside this subdomain. Then we can compare the prediction from my G delta. So this will be loss function. Or roughly speaking, if my G delta is the ground truth, then it will be a fixed point of the G delta. Or for another point of view, my G delta is like a PDE. It's a constraint of the physics. So this is a loss function. But also, for sure, we also need a boundary condition and an initial condition to predict a specific solution. That's always given. Initial boundary condition is always given. So this is one testing example, a 2D Poisson equation, linear Poisson equation in a circle cutout. Then after training, this is one testing case. For example, this is a ground truth. So this is F of a new testing case. This is ground truth. This is a prediction and this is pointwise error. So it's pretty good. Also, this method, because we only train the G delta locally, which means when we train this G delta, let's say for circle with a specific size, then when we try to apply this G delta, we can go beyond the training geometry. The circle can be larger, can be small, unless it's the same PDE. We can do this framework. So we have much better generability compared to standard end-to-end training. Or we can go to a PDE system, right? Two variables, C and CB, we can apply the same framework. So this is how can we solve this extreme a task of one data point. And in the last topic today, I will discuss another area we are currently working on called generative modeling. This is area I believe many of you have know this. We can apply this software for the ChatGPT to generate an image or different diffusion model to generate an image. For example, on the left, but this is we apply a network. This is just commercial software to generate an image. This is my postdoc who did this work. But after we input a few different images of him and generate a new image. But here we try to go beyond the generating of images of cats or dogs or humans. We try to go to physical simulations. We try to generate solutions of PDEs. Oh, by the way, here's kind of in the drone market. So specifically, the generative model here, we applied its diffusion model, which is a really hot topic nowadays. So in diffusion model, we have the forward process, but by adding the noise into my data, for example, a cat, until it becomes a pure noise. So this is the forward process. Then we can do the reverse process. So after training, we train the score function. Then in the reverse process, we also then we remove gradually the noise until we recover or generate a new image. So I will not go details into diffusion model. But there are lots of work in this area already. But why we have to develop something new for physical simulation? For three reasons. So one is the existing diffusion models. Usually people consider discrete output or image 100 by 100 pixel. It is discrete. And in many cases, it's in fixed resolution. But you can only generate a specific resolution. However, in PDEs, in many cases, we try to generate a continuous function as a PDE solution. But in the same philosophy as operator learning, we do not want to limit it to a finite resolution. We try to generate PDE solution at any location of Y. Also, the standard data-driven learning well, there's no way to obey the physics. When you train a network using the data, for example, generate the flow in this picture here, there's no guarantee this flow is a solution or is a valid solution of the Navier-Stokes equation. So we try to address these issues. So the framework we proposed is called FUNDIF, the function diffusion. So the basic idea actually is not complex. So 3 steps. Because we try to generate a function, again, a function in infinite dimensional space, so we have to reduce infinite dimensional space into a finite dimensional space in practice. So let's say we have an encoder and decoder. Well, this encoder and decoder maps this function any f to a finite dimension latent space RD, the D dimension embedding. Then we can do a latent diffusion in this latent dimension, well, in this RD space. So this is the basic idea. But for this framework, so first we try to see what's the error. So let's assume our ground truth distribution, well, in this infinite dimensional space of squared f is p. And by using this 3-step procedure, well, encoding, latent space diffusion, decoding, we go to another distribution called p hat. What's the distance or what's the error between p and p hat? So what we can prove is that the W1 distance between p and p hat can be bounded by 2 terms. The first term is error from the autoencoder. You can see this is the encoder, this is the decoder. It's essentially a conjunction error. How well this latent dimension and your encoder decoder captures the original space of functions. Then the second error is the latent diffusion. This W1 distance, so sorry, the small p and the small p hat is the ground truth and generated diffusion in the RD space. But this is the error of your training of the latent diffusion. Also, there's a scaling factor here. This measures is the Lipschitz constant of a decoder. So a smooth decoder is usually more robust. So these are the 3 errors, pretty generic error bound. And you can see here, this is a balance between these 2 errors by using different dimension of D. Ideally, to have a good reconstruction, you should apply a large latent dimension D, right? If D is large, then encoding and decoding is easier. But if you have a large dimension of D, then the latent diffusion becomes harder. But if you try to a small dimension of D, your encoder decoder is worse, but the diffusion is easier. So there's a trade-off between these 2. And more specifically, well, previous is just a generic example for any distribution P and P hat. But here, let's consider a very special a space called RKHS reproducing coherent space. So in this space, let's assume any function f is written as a summation of eigenexpansion. So this for I is an eigenfunction. These are some coefficients. And also we consider all the functions are in the unit ball, right? They are bounded in the ball. And we also add another assumption. So this eigenvalue, the mu I, has a decay of this polynomial decay. So otherwise, the space is just too large for analyze. Okay, given this setting, my encoder is pretty naive. I just do the truncation of the top D eigenfunctions. Decoder, then we just reconstruction from, again, the top D functions. But encoder, decoder, there's no network here. Simply truncation. But what we can show is in this example, and using the previous method, so my distance between P and B hat can be bounded from below by 1 over log n. So the n here is the number of training points. We assume we only analyze that the error was the number of training points, not network training. So and so we have the upper bound, which is log n over log n. So only difference between this upper bound and lower bound is log n here in this term here, which is in general pretty small. So which means in this framework, we have achieved this minimax optimal rate in terms of number of training points. We also have other spaces in your paper, but this is just one example. Okay, now let's look at how can we implement this in practice. So again, 3 steps. First step, we train an encoder and a decoder. So this is my encoder, this decoder. So my encoder function, this is my any function f. I just draw a picture here. This is my function f. Then we go to this encoder to some later dimension. Then we do the decoder. Just a few points to know that is. So first, we try to construct this function again in any location y. Sorry, x here is the location of x. So this is the same as DeepNet. We add this query location into my decoder. Now for my decoder, we can predict of output my function at any location of x. This is similar to operator learning that I explained at the beginning. And also we try to handle the functions of different resolution, different discretization of the input. And we apply this technique called the perceiver, right, from the literature, to have basically essentially this sort of a cross attention, so we can apply arbitrary resolution of this input function f. So this is the first step. The second step is the training of the latent diffusion. Okay, pretty simple. Well, you go from a true image, then you go to this encoder, go to a latent space, then in latent space, you apply the diffusion process. You can apply any diffusion method you like. For example, standard DDPM or DDIM or flow matching. We also apply flow matching in another paper. So any method you can apply to here. Also, we can apply other, for example, if you have some condition, if you have a similar condition, we can apply conditional diffusion also into the latent dimension. Oh, one thing I have to mention, so we can also incorporate physics into my encoder training, decoder of the training, because we have x as input, we have the solution as here, then we can compute the PD loss. Okay, using automatic differentiation. Okay, that's the 2-stage training. After training, we can do inference, we generate a random sample, we go to diffusion, go to latent dimension, latent value Z1, then do decoder to get the output, one sample. Actually, I didn't plot the x query location here, but because we have the query location, so we can get continuous function at any location. Then this framework, well, this is just generation. We can apply this framework with small modification for different downstream tasks. And here I just show you one example. Well, this is a Kolmogorov flow with the equation here. So what do we try to do? Well, this is just one example of velocity of u and v. Okay, we try to generate physically consistent velocity field. For example, they must be divergence free. Then we can have encoder and decoder. But for example, when we try to impose a periodic boundary condition, this can be easily imposed. We just do a transformation to this decoder, go from x to cosine and sine. This is a standard technique people have applied in physics information networks. Essentially, some kind of free embedding, they can guarantee your generated function is always periodic. And also, we have the universal approximation theory. And also, by using this specific transformation, we can have divergence free, or you can also put it in the loss function. You can put it in the loss function to compute what's error of divergence. Or for example, training with PD loss. Okay, so after training, this is a generation, unconditional generation. We generate a new flow. So on the top, what is the generation with the physics, with the divergence free constraint. So these are two samples, true samples. This is 3 samples of generated samples. And if you compute divergence, they are purely 0. Or if we do purely data driven, no physics law, then if you compute divergence, you can see it does not satisfy this physics law. Because we can obey the physics law, then if you look at some other metric, for example, energy spectrum, which is standard for analysis, definitely is more accurate. Not surprising. Okay, now let's look at downstream task, which is reconstruction from noisy and low resolution input. So let's assume, okay, this is a little bit small plot here. So let's say this is we have the velocity at low resolution. For example, 1x, 2x, or 4x downsampling. So it's downsampled velocity field. And also we add a 20% noise to this downsampled input. But you can low resolution noise input, then we try to reconstruct high resolution, a clean solution of the flow. Essentially, it is a modify the previous procedure from unconditional generation to conditional generation. And the condition is this noisy input. Then we can compare with a lot of baselines. We have many baselines here. Some baseline are end-to-end training. For example, you just train an end-to-end model. Input is low resolution input. Output is high resolution image. End-to-end training. Or you can apply some other techniques, also diffusion-based technique. So these are some examples here. So this column is our method, FONDIV. It's pretty accurate. And they are all the baselines. For some baseline, so you can see here, this baseline is end-to-end training, for example, FLO or VIT, Vision Transformer, or this method called deport. For end-to-end training, usually they cannot generate really clean output. Still you can see it's noisy. Because the really is we have a really large noise level. For diffusion-based, usually can generate more clean output. But because you try to generate a similar pattern from your prior. But still the error in general is cannot be guaranteed. For example, in this case, generate a pretty strange plot. It cannot bear pretty good physics. And here is just more metrics here. This is the error of L2. And you can see we can go to a different resolution. So the last bar here is our method. You can see it's always better than other methods. If it's high resolution, then for example, this method is CVIT. Another vision transformer, she can still have good accuracy if it's high resolution image, right? But in general, diffusion model would work better. Okay, this is the one application. Well, this application this method can be extended to also other applications. For example, complex geometry. Right? In the beginning, I mentioned operator learning for complex geometry. We can also modify this framework to handle complex geometry. We call it the geo-form flow. But if we have complex geometry, then similar procedure, encoding, decoding, but we only need an encoding or encoder network that can handle complex geometry. So many ways to do it. Here we follow this idea similar to the point net. We use a point cloud to represent a complex geometry. We send a point cloud plus a FONDIV remote. Then we can do this complex geometry. For example, again, this is also an example of reconstruction. You can see this is my input. It's a pretty sparse resolution, a pretty sparse measurement of the flow. This is ground truth. Now we can reconstruct. This is our method. We can reconstruct pretty accurate flow field compared to reference. And here are another two baselines. So these are different benchmarks. Yeah, they work well. Lastly, I do want to show you one software for device D. So many of these examples are implemented based on this software. It's for scientific machine learning, especially for where you have PDs, physics-informed learning. We are currently still working on this and adding new features. It's open source in GitHub, easy to use. Yeah, feel free to apply this software to your research, or if you have new idea. We are also welcome to add a new feature and incorporate it into the library. So with this, thank you for your attention.
For Dr. Lu's wonderful and very well informed seminar. So any question from the audience?
Thank you for exciting presentation. So my question is about DeepNet.
Yes.
So I know you have two network to process your two input, right? So one is branch net, one is the trunk net.
Yes.
So my question is, what's your motivation have to like two network to process these two input and could you give me one specific example of the two input?
Okay, so first the motivation. So our very initial motivation, actually some motivation I showed here, right? This can have a really good relationship with the traditional method. But our very initial motivation is from the theory. So although I didn't show the theory here, but this is a theory paper for this operator learning. And based on the theory, or based on the construction in the theory, this is the approach they applied. Essentially, our initial network is motivated by the theory. Then, but here, you can see we can do lots of modification on top of this. Then for multiple outputs, if you have multiple outputs, there are a few ways to do it. One way, or a simple way, is you can have multiple branch network. The reason is your different inputs may have different dimension, different geometry, or different shape. So it's pretty flexible to apply each to apply a single branch net for each input. Then essentially have multiple branch nets. They have multiple embedding of the branch nets. Then try to combine all these informations. So that's a simple approach. But this is simple approach is also guaranteed by the theory. Actually, we have people to show. Well, when you have, let's say, two inputs, now you have two embeddings, or B1, maybe C1. Then you have a trial net of T1. You have three vectors. How can you merge the three vectors? So one way is using the tensor product. Well, instead of standard dot product, you can use tensor product. Or you can also use similarly the dot product. It's also theoretically can be guaranteed. So this is the simple extension. For some specific application, for example, in this geocarbon saturation, so we have multiple inputs. But here, all these inputs, they are in the same dimension, same shape. Then the easier way is to combine these different inputs as different channels of the input, the same as the image applications where you have RBG channel. So here you can have three channels. Then just put the three channels together as a network input as a one branch network. It also works.
Thanks for your insightful talk. I just have a questions regarding to your recent work about the diffusion models.
Yes.
So I think high-level ideas for these two applications is for, I guess it's for like a non-intrusive measurement, so we can get more high-resolution solutions. And I'm just thinking about whether it is possible that when we doing the training of a diffusion network, we also include the basis functions in it, so you can directly plug this diffusion models in your like a pin network. So that may solve a more broader topic on the PDE application.
So you mean add a
So
basis function in which part, either in the diffusion part or in the encoding decoding?
So I think because in this training framework, we don't have basic functions nor like initial condition, boundary condition.
Correct.
So we cannot make use of the basic functions from what we can get in general. So let's say if in our encoder we can somehow replace some part or add in the part that we can include the basic functions, then during the samplings we can do conditional generations based on our basic functions. Let's say the y in our equalnet, and then we can apply like the pins and we can derive the derivatives for the basic functions. Then we can do the better reconstructions as well.
Yeah, I would say yeah, definitely correct. So this is in this paper we didn't do that, but yes. So if we try to apply this more broadly, let's say for PD solving or some other tasks, if you have boundary condition, inner condition, or any other conditions, we could apply this into the framework. So this is just one basic framework, but there's also modification we can apply to this. Yes.
Sure.
Yeah, thanks for your great presentation. I just have a general question. So for operator learning, it works in the function space, so it's infinite dimension. So in practice, we may think we want a model to be resolution free. So in community, it seems this property is very important, and I'm just wondering your thinking about it, and why do you think this is important?
I mean, why we need divergence free or?
Resolution free.
Okay. So a few reasons. So one resolution free is, or maybe I can just use as this picture as to demonstrate. So in many cases, when we train my network, I may not have a one data set in the same format. In some cases, we may have a data set, let's say with resolution 100 by 100. I have another part of data set with resolution, let's say 70 by 70. So if my network cannot be applied to a different resolution, then you have to do some pre-processing to align different data sets in the same format, which is okay. Actually, we do this in some applications, but it's less convenient. So this is one thing. It's more flexible to handle data sets with different resolutions. Then another thing is, well, for that's the training. That's for the prediction. One nice thing when we can predict the PD solution at any location is that it's really convenient for some downstream tasks. For example, in the topology optimization, when we try to apply the tree network to the downstream task of minimize the objective function, and then in the objective function we have this integral, and when we compute, then we have to compute in the integral using some numerical methods. For example, using some quadratic points. Then if my network can only predict in a grid, but you cannot compute the value at a quadratic points, we have to apply some interpolation. But if my network can predict at any location y, it's very convenient to apply any quadrature location or to compute gradients. So it's pretty flexible. Yeah, basically it's more flexibility. I would say it's not essential in some cases, but it gives you more flexibility.
Thank you so much.
Other question? Oh, I may have a quick follow-up.
Sure.
I saw you show a very nice mathematical proof. Do you have any assumption on the distribution of the training data? The one you showed the arrow bound for
This
the,
one?
yeah. You basically you're using the proof similar to like a PCA. Yeah, just interesting to know you assume M data.
Oh, okay. Yeah, the data here, we assume the data set has size n and they are IID sampled from the distribution P. So it's IID samples. Yeah, I did write down here. So yes, this is a standard assumption. So yeah, IID. Yeah.
Sure. Any question from the audience? Okay, if without further question, let's thank our speaker again.